In this slide and onward, we will talk about the use of Taylor series for the taking derivative or predicting the derivation or differentiation numerically. Sometimes up to this point, we actually assumed that the derivatives are available for the exact function. That's why we were able to use them in the Taylor series expansion. But what if they are not available or not easy to take? We need to use differentiation, numerical approximations for differentiation. And we can use Taylor series. We showed this earlier while trying to explain the remainder term, Rn term. We showed that the differentiation can be taken by using Taylor series. And we can actually expand the Taylor series in 3 ways to approximate the numerical differentiation. And these are all called finite divided difference approximations because they include the difference between the first or the current and the previous values. So these 3 are called forward difference approximation and finite divided difference, or backward difference approximation, or centered difference approximation. And we will see the difference approximation for the first derivative in this section, but these can also be used for higher derivatives than the first one. Actually, we will show the second one as well, but mostly the first derivatives are the mostly used because they are the simplest ways, and they can give pretty good results, especially the step size is small enough. So let's focus on these 3 in the following slides. And the first and most widely known numerical approach for taking the derivative is forward difference, and we will consider the first degree. And for that, we can just use the first degree Taylor expansion. Let's write down the n equals 1 Taylor expansion. And we know that it is fxi plus 1 equals fxi plus f derivative xi times h plus r1, the remainder term. And if we just isolate fxi, this term, isolate here, this is equivalent to, you can see, fxi plus 1 minus fxi divided by h and minus r1h. And we said this is actually OH. We already mentioned about this before, but here we wanted to make you remember this, so that you can see this is the derivative estimation. And because we use the current and previous, or the next and current, it is called forward difference. And if we make it short by giving a delta value for the difference of this, we can just simply write the forward difference. The derivative is estimated as delta fi divided by h plus, and r1 divided by h is on the order of h, that's why we call it OH. Simply, this is now the first forward difference. First forward difference. And this is step size. This is the difference, delta. And the entire term is called, first finite divided difference. Actually, first forward finite divided difference, we can say also. Forward finite divided difference. And we use forward because the data at I and I plus 1 are used. Forward because I and I plus 1 are used. And if we try to show this graphically, let me draw a graph here. Like this. Assume that this is our function and this is the first value, xi value, and this is the xi plus 1 value. And we know that the true derivative is for xi, let's say, this is the tangent true derivative, meaning f xi, because xi is this, f xi, this is fx, and this is x. So, and the blue line is the first derivative. But the approximation states that the derivative can be estimated by combining the f values of xi and xi plus 1. We mentioned this in the prediction of the remainder term as well. You can go back to those slides or videos. And here the idea is the same. We say that combine these with a line. And this is approximation. And this is h, by the way. And this is the delta fi. So the slope gives the approximation. This slope, delta fi divided by delta fi divided by h, is the approximated first order fxi or fi. And because the remainder term has only h value here, or here also we can see h, halving the step size halves the error. And let's write down the final formulation here. F xi tilde is equivalent to delta fi divided by h. H means halving the step size halves the error. So this is the forward difference. Let's move on and check the other derivative estimations. For the backward difference, we simply expand the Taylor series backwards. We can just write it down. Expand the Taylor series backward. And we can do this by simply changing fxi plus 1 with xi minus 1. So we will write it backward. And we can still predict this by the fxi value minus the derivative xi h plus f second derivative xi 2 factorial h square plus, and it goes this way, like to the end, to the infinity. Oh, basically, because this is just an backward expansion, there is a negative sign here. So we subtract the second term, then sum the third term, then also subtract the fourth term. So we have a sign change in every term. We should be careful about this for the backward difference only. In the forward difference, it's always plus, but in the backward difference, plus minus it goes this way. So we truncate from here, and we will have the first order backward difference this way, truncating after the first derivative, first order term, and isolating the derivative fxi. If we isolate fxi, the result is like this. Fxi is equivalent to fxi minus fxi minus 1 divided by h, and also there is the remainder term rh, which gives us, in short, delta fi. But before that I should show that because this is minus, we moved this to this side actually and took this to here, so it's fxi minus 1 divided by h, because this has h, and r1 is the remainder terms. We can write this way, and this is also delta, but because it's current to previous, or we are using just backward, it's just reverse delta sign. We can write like this. In the forward it was the regular, this one, but in this, because it's backward, it is just the reverse delta sign, like this. Fi divided by h plus OH. This truncation error is again in the first order, h. And if we try to explain this graphically, let's draw the graph again here. Again, fx and x, and we have this function again. Let's say this is xi, this is xi plus 1, and this is fxi. Actually, this is wrong. This is forward. We need to make it backward. This is xi minus 1. This is xi. And this is xi minus 1 function value. And this is fxi function value. Because it's backward, we need to write this way. And the difference is again h. And we try to find the derivative of fxi. Don't forget that. Always it's xi. So xi is here. We want to find the derivative of this. So the derivative is this blue line. Let's say this is the derivative, true derivative, which means f prime xi. But we approach this going backward between the function values of xi and xi minus 1. So we combine these like this, or actually backward from right to left. And this is the, and if we see, this is the reverse delta fi, and the slope here gives us simply the prediction for xi is delta fi divided by h from the geometry actually, and this is the approximation. And this is called the first backward difference. And because of this truncation error is only the linear h, or here also it's linear, meaning halving step size just halves the error. So in terms of having the accuracy, the backward and forward difference are about the same, similar in magnitude, because the magnitude of error is linear. Let's move on to the center difference in the next slide.